Welcome to medians and altitudes of triangles. Today's objectives are to apply properties of medians of a triangle and to apply the properties of altitudes of a triangle. In this picture we see a median drawn in a triangle. Now the median of a triangle is a segment whose endpoints are a vertex and the midpoint of another side. So our definition for the median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. Now, in a triangle, there are three medians. So here's one of them. I'll draw another one over here. So I'll start on this side to show you that these two sides are being split. And there's two medians. And then I'm splitting the side AC. So these two sides would be congruent. And there's a third median. Now, medians are concurrent, and you can see they intersect right here. And the point of concurrency of medians is known as the center of gravity. So medians are segments whose endpoints are a vertex and the midpoint of the opposite side, and they are concurrent, and their point of concurrency is called the center of gravity. Another name for the point of concurrency is the centroid. Using the centroid theorem will allow us to figure out the lengths of the segments within the median. So the centroid theorem tells us that the centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So, for example, let's look at this segment right here. So what this is saying is that this length of AP is 2/3 of the entire segment AY. So if I had, let me just draw these out here, say this is AP, and then extend it a little bit and say this is Y. So what this means is, if I told you that AY was 6, and I wanted to figure out what AP was, I know that AP has to be 2/3 of 6. Or AP needs to just be 4. Which makes sense because 4 is 2/3 of 6. And this is the centroid theorem. Now let's use the centroid theorem to find segment lengths. In triangle ABC, segment AF is equal to 9 and segment GE is equal to 2.4. Let's find each length. So here we want to find the length of AG. Now we know that AG has to be 2/3 of AF. So if we want to find segment AG, we know AG has to be 2/3 of AF. We know what AF is, so AG equals 2/3 times 9. AG is going to equal 18 over 3, or just 6. Now let's find the length of CE. So, using the centroid theorem, we know that segment CG has to equal 2/3 of CE. Now the only information that helps us here is that GE equals 2.4. Now since we can't directly plug in GE to our equation here, we have to use the segment addition postulate and plug in this value of GE. So we know that this entire segment right here is made up of two segments. So we know that segment CG plus segment GE equals the whole segment CE. Now this is helpful because now we have a value of GE we can plug in for. We know what CG stands for, and what we're trying to solve for is CE. So now what we're going to do is since we know what CG is, we're going to plug in this value right into here. So our equation is going to look like this. 2 over 3 CE plus GE equals CE. Okay, so now we want to subtract 2/3 from both sides, and we have GE equals 1/3 CE. Now we know what GE stands for, it's 2.4. So we'll just plug that in right down here. So we have 2.4 equals 1/3 CE. Now we have to isolate CE, so we multiply both sides by 3. And our final answer is CE equals 7.2. The key step for this problem is using the segment addition postulate. Because once you do that, you can plug in for your value of GE and solve for CE. Let's do a few more practice problems using the centroid theorem. In triangle JKL, ZW equals 7 and LX equals 8.1. Let's find each length. So, using the centroid theorem, we know that this segment right here is going to be 2/3 of the entire segment KW. So we know that KZ is going to equal 2/3 times KW. Now we don't have any information directly plug in, so we have to use the segment addition postulate. So we know that KZ plus ZW equals KW. So we can plug in 2/3 KW right here for KZ. We know that ZW equals 7. And since we're solving for KW, we can leave that as a variable. So we'll get 7 by itself. So we'll say 7 equals 1/3 KW. We'll multiply both sides by 3, and KW equals 21. For part B, we're looking for segment LZ, which is right here. So we know that LZ has to equal 2/3 of LX. Now we do have something directly to plug in for LX, so this one's a little easier. So we have LZ equals 2/3 times 8.1. We multiply those together, and we get 5.4. So just remember, it's the segment from the vertex to the centroid equals 2/3 of the median. So here we have this mobile contraption that's used to balance the structure. Now, what we want to do is we want to use our knowledge of medians to help us find the center of gravity to help us keep this contraption balanced. And you remember that we called the center of gravity the centroid. So we're going to use our knowledge of medians and centroids to help us find the center of gravity of a mobile. Here we have a diagram that shows the plans for a triangular piece of mobile. Now the sculptor wants to attach the support of that mobile so that it's balanced. So we have to figure out how to balance this mobile. Now the whole idea is to figure out what the center of gravity is, which we know as the centroid. So we're finding the centroid. Now we know the centroid is where all the medians intersect. We know a median is a segment that goes from a vertex to the midpoint of the other side. So the first step is to find the midpoints. So I'll find the midpoints of segment PR. So I take the average of my x values and the average of my y values. And for a midpoint, I get 9/2 and 2. I'll find the midpoint of QR. The midpoint of QR is 0 plus 6/2 and 8 plus 4/2. Which equals 3, 6. The last one I have to find is QP. So QP is 0 plus 3 divided by 2 and 8 plus 0 divided by 2. So that midpoint is 3/2 or 1.5, 4. Now let's plot these midpoints. So the midpoint of PR was about 4.5, 2. That's about here. The midpoint of QR was 3, 6. And the midpoint of QP was about 1.5, 4. So right about here. So these go from their midpoints all the way down to the vertex. So you go from the midpoint all the way to the vertex, from this midpoint all the way to the vertex. So here we see that these intersect perfectly right at this point. So the sculptor should base the centroid at 3, 4. So the steps are, first find the midpoints, draw them on your coordinate plane, and then find what the centroid is. The altitude of a triangle is a perpendicular segment from a vertex to the line containing the opposite side. So we were learning about medians and centroids before. Now we're going to learn about the altitude of a triangle. So the altitude of a triangle is a perpendicular segment it goes from the vertex to the opposite side, and every triangle has 3 altitudes. You can think of the altitude as the height. Now the altitudes can either be inside, outside, or on the triangle, depending on the type of triangle. So here it's a perpendicular segment from the vertex to the opposite side. So there's 1 altitude, there's 2, and there's 3. Now these don't have to split up the opposite side. All they have to do is be perpendicular to that side. Now these intersect and have a point of concurrency. That point of concurrency is called the orthocenter. So the altitude of a triangle is a perpendicular segment whose vertex goes to the opposite side. The triangle has 3 altitudes, and the locations can be inside, outside, and on, and the point of concurrency is called the orthocenter.